When a model is loaded, it deflects, and deflections in the members may induce secondary moments. This is due to the fact that the ends of the member may no longer be vertical in the deflected position. These secondary effects for members can be accurately approximated through the use of p-delta analysis. P-delta effect is also known as geometric nonlinearity. It occurs in every structure where elements are subject to axial load. P-delta is actually one of the many second-order effects. It is a real effect and is associated with the magnitude of the applied axial load P and a displacement delta. There are two types of P-delta analysis. P small delta is associated with local deformation relative to the element chord between end nodes. P big delta is associated with displacement relative to member ends. P delta involves the equilibrium and compatibility relationships of a structural system loaded above its deflected configuration. Several building codes require the use of a proper design method to consider instability and second-order load effect problems for individual system elements and entire structural system. Various methods are available to assess stability design. The following calculation procedures are presented in this study. 1. A simplified method is developed for the P-delta analysis in regular frames under the effect of constant axial loads to obtain story drifts and end moments. 2. The presented analysis method can be applied to an entire building or an individual story. 3. Column effective length factors are obtained for individual columns. In addition, design tables are presented. Proposed story-based design method enables design and/or control of any story of a building independent from other stories. Story-based design can also be utilized during member selections of the story. It can also be used to cross-check results derived through software. In this study, a simplified approach to analyzing regular moment frames is developed by considering second-order P-delta effects. These are 1. A simple relation is obtained for the column shear force under the P-delta effect. 2. Column end moments are obtained under the P-delta effect. These are obtained for the individual columns of the story. The analysis of individual columns of the story gives better results than the analysis of a whole story of the structure. 3. The column effective length factor K of an individual column is obtained by utilizing the relation between stiffness coefficient C2, which is related to the P-delta effect, and the flexibility parameter lambda. Moment amplification factors of P-delta effects are presented. And lastly, the presented analysis procedure can be applied to an entire building or any individual story. It's story-based design. The results obtained using the proposed method enables second-order effects coincide with the results of software analysis. This is the first report of a simple equation for the shear force delta relation as in column under second-order effect. Story drifts can be calculated using these relations. End moments of the story columns can be calculated using the presented amplification factors. After that process, beam end moments can be calculated using any approximate or exact method. Calculating closed-form solutions of K factors is complex. However, this calculation becomes possible by using the presented tables. Proposed story-based analysis method makes the second-order analysis possible of an individual story which is not dependent on the entire building. This case creates a user-friendly design format. Proposed design method can be applied in a wide range of frame structures, but should not be applied for shear walled structures, because of end forces of shear walled structures are not appropriate for assumptions of frame structures' idealized conditions.